Hello everyone, this is Workshop 6, Combustion Analysis and the Empirical Formula. Now, combustion is the process of taking a sample, generally an organic sample, an organic sample being something containing carbon and hydrogen, and burning it in the presence of oxygen. Now, when you burn that sample in the presence of oxygen, you're going to create two products. You're going to create carbon dioxide, and you're going to create water. And now, by taking this reaction, you're able to find out information about your starting sample. Through the analysis of this problem, we can get the empirical formula of what we're starting with. That's what all these problems are going to be looking for. You're not going to be told what this sample is. You're going to be told the components of it, like what atoms comprise it, like if it's just carbon and hydrogen, or if it's carbon, hydrogen, and maybe oxygen as well, or some other element added into it, but you won't be told the actual formula. And so you have to figure that out from the problem. And so there's a series of steps that we follow to go from information about our products to get information about our sample. So step one, since we're trying to get a formula, formulas tell us about molar ratios in the compound. Those subscripts tell you how many moles of each element are needed to make up that compound. And so first step, if you are given masses for your product, you're always going to convert the mass of your product into moles of product. This way we're actually able to use it to find our empirical formula of starting sample. So grams of CO2 become moles of CO2, and grams of H2O become moles of H2O. So now we are in moles, and moles allow for a lot more conversions between different substances and between atoms. The sample does not contain carbon dioxide and water, it contains carbon and hydrogen. And so we can use our moles of each product to get moles of individual atoms. You are able to go from moles of carbon dioxide into moles of carbon, and you're able to go from moles of water into moles of hydrogen. And that is due to the molar ratios told to us by the formula itself. If carbon dioxide is CO2, then there is 1 mole of carbon needed to make 1 mole of carbon dioxide. It's a 1-to-1 ratio. In water, if it's H2O, that 2 subscript tells us that we need 2 moles of water to make 1 mole. 2 moles of hydrogen to make 1 mole of water. It's a 2-to-1 ratio. Get rid of this 2, sorry. It's a 2-to-1 ratio of hydrogen atoms to water itself. And so by getting our products into moles, we can convert between moles of the entire compound to just moles of the atoms that comprise it. Now, if the sample just has carbon and hydrogen in it, you can move on to the next step of your calculations, working on getting that formula made. But a lot of compounds are not going to be just carbon and hydrogen. You're often going to have a third, maybe a fourth element added in there as well. And that is where going back to our mass of everything is going to be very important. If your compound has an element other than carbon and hydrogen, you're gonna have to find the mass of this other element. And rather than writing it out, I'm gonna use numbers instead. I feel like it makes it a little bit easier to understand what we are talking about. Okay, find mass of missing element. Now what I mean by that is that if there is some other element in the original compound, then you will know the mass of your original sample. Let's say we started with 10 grams of our sample. Now, we know that our compound has carbon and hydrogen in it, that's for sure, and it has some third element that we don't know any information about right now. But if we have moles of carbon, then we know we can get grams of carbon. And if we have moles of hydrogen, we know we can get grams of hydrogen. Let's say when we convert this into moles of carbon, we are then left with 2 grams of carbon and 3 grams of hydrogen. And we know that our sample originally had 10 grams. And so if all of our carbon is 2 grams of the sample, all of our hydrogen is 3 grams of the sample, the rest of the mass must be the mass of the third element. And so if we do 10 grams for the original minus the mass of the carbon and the mass of the hydrogen, the mass that is left has to be the mass of the third element. And if we can go from moles to grams here and here, then we can go from grams to moles. So you find that missing mass from the mass of our carbon and hydrogen, and then we take our 5 grams and convert it into moles, because again, we were working with formulas. We're trying to make an empirical formula that tells us molar ratios. The mass itself does not help us find the empirical formula. So now once everything is in moles, you can start writing out what's called your pseudo formula. If you have just whole numbers, that makes it a lot easier, but oftentimes because we are converting from grams to moles and we're doing all these calculations, you're not going to have clean numbers for your subscripts. And that is fine to start with. That is going to help us differentiate between the different atoms, and we're just going to write whatever decimals we get. We're going to write our pseudo formula. Using the moles of each of the elements in our subscripts. Moles of each element as subscripts. So we write our pseudo formula, we have our subscripts plugged in, no matter how big the decimal is. And now, once we have our pseudo formula, this empirical formula is comparing the molar amounts of each atom to each other. And so we have to divide all of our subscripts by the smallest value there. We're going to divide all subscripts by whatever your smallest subscript ends up being. And now again, this might give you just whole numbers. They might all be perfectly divisible by each other. And so you would stop here, you would have your final formula. But again, oftentimes you're going to be left with decimal places. And we can't have decimals in our empirical formulas. Since it is ratios comparing to each other, but since it is molar ratios compared to each other, and since we're saying that we have this much carbon bonding to this much oxygen to form a compound, or this much carbon bonding to this much hydrogen, you can't have part of a carbon atom. You have to have a full carbon atom to form the bond. There's no such way as having only part of an atom. And so if you have decimals, this is where you're going to have to be comfortable with seeing decimals and comparing them to fractions. Because if your subscripts are not whole numbers, are not whole numbers, we're going to multiply by the smallest whole number to get whole subscripts. Multiply by smallest whole number to get whole subscripts. Your final answer should never have decimal places in it. Your subscript should never be decimals. So just to give some examples, let's say you have 2.25 0.25 is equal to 1/4. You can multiply this number by 4, and you would get a whole number. Let's say you have 3.6. 0.66 is equal to 2/3. 3 is in the denominator. You can multiply this entire number by 3, and you will get a whole number. So that's what I mean by like getting comfortable with seeing decimals and knowing what fraction they compare it to, because it makes it easier to know what number you should be multiplying by rather than trying to guess and check each single small number to see what works. For homework questions and exam questions, all of the numbers generally are able to be multiplied by a single whole number, and you get all of your subscripts as whole numbers. It's not very often that they would have you multiply by multiple numbers and have to do that guess and check method to get a formula. In the lab though, for anybody taking 102 or 103, it is more common or more likely that you're going to have to use that method, that you're going to have subscripts that don't perfectly work with each other and multiply by multiple different whole numbers to figure out what your final empirical formula is. And so now, if they only want the empirical formula, you would stop at step 5, but there is a chance that they will give you the molar mass. Because remember, empirical formula is the simplest form of an equation. The empirical formula just tells you the smallest ratios of each atom. Once all of your subscripts are divisible by 1, then you know you have your empirical formula. Only divisible by 1. Then you know you have your empirical formula. But a lot of compounds are not going to be that simple. They're going to be able to be divisible by 2 or 3 or some other number to make their empirical formula. And so while the empirical formula is the most simplified version, the molecular formula is the more accurate version, is the actual correct comparison of the elements to get the specific compound that you're looking for. A lot of different compounds can have the same empirical formula, but can have completely different molecular formulas. And so the molar mass can help with that because you're able to compare the mass of the empirical formula to the mass of the molecular formula, which would be the compound's molar mass. So if the molar mass of a compound is given, you can then determine your molecular formula as well. All you have to do is compare mass of empirical formula to molecular formula. If the mass of my empirical mass is 25 grams per mole, but my molar mass of whatever compound I have is reported to be 75 grams per mole, EM to MM, empirical mass to molar mass, has a ratio of 1 to 3. And so whatever your empirical formula is, you would multiply it by 3 to get the molecular formula. So the steps seem long, but a lot of this is going to get repetitive with practice. A lot of the steps are going to be the same across all types of combustion analysis questions, especially these steps up here, steps 1 through 3. You are expected to do steps 1 through 3 basically every time you do a combustion analysis question. Or actually steps 1 through 5, really, because they're always trying to make an empirical formula. And so you're always going to be going grams to moles of our products, getting from moles of carbon dioxide and water to moles of carbon and hydrogen respectively. This step is only if there's some other compound, but either way you're always getting those moles of carbon and hydrogen, writing your pseudo formula, dividing by everything, getting your proper formula. Step 6 doesn't appear all the time. You might not have to do this very often, but steps 1 through 5 are always followed, and steps 1 through 5 get repeated the most. The ratios that you're going to use in steps 2 and the sub-step of 2 are going to be the same. The calculations and the conversion factors you use for step 1 are always the same, and so a lot of this becomes a lot clearer to follow with practice. So let's get into some practice problems. Question 1 has us looking at the combustion of petroleum. Now, petroleum is important to know that that is what is called a hydrocarbon, or a compound that only has carbon and hydrogen in it. So for this first question, we don't have to worry about another element being present in our sample. We just worry about carbon and hydrogen. And so we have 12.501 grams of our petroleum. I'm just gonna write sample, I don't wanna write the whole word. And then after combustion, the petroleum produced 38.196 grams of carbon dioxide and 18.752 grams of water. So a previous analysis determined that the compound does not contain oxygen. So they even told us in the problem that is not going to contain oxygen. Establish the empirical formula of the compound. So we know the mass of the sample, we know the mass of our carbon dioxide and our water, and we know that it's just carbon and hydrogen that we are concerned about. And so our pathway, converting grams to moles, and then moles of one product into moles of the atom that we are focused on. So let's start with our carbon dioxide. We have 38.196 grams of carbon dioxide. If we want an empirical formula, we need to convert this into moles. Grams is in our numerator, so we want grams in our denominator when converting. Remember, to get from grams to moles, you need your molar mass. The molar mass of carbon dioxide, you're adding together the mass of 1 mole of carbon and 2 moles of oxygen. You should get about 44.01 grams. If your number is rounded a little bit differently, that is fine, but 44 should be the same across the board, unless your decimals are like really high over here. But somewhere around 44.01 grams. And that is for every 1 mole of carbon dioxide. So that will get us from grams to moles. And now for our sample, we care about the carbon. Carbon dioxide contains 1 mole of carbon in it in the entire compound. And so we're going from moles of one to moles of another. Moles of carbon dioxide is our numerator, so we're going to put moles of carbon dioxide in our denominator. And this is a 1-to-1 ratio. There's 1 mole of carbon needed to form 1 mole of carbon dioxide. And so the math itself is just 38.196 divided by 44.01. This much carbon dioxide came from 0.8679 moles of carbon. And now we're going to do the same work with our water. 18.752 grams of water. Again, we have to convert out of grams and into moles to work with our empirical formula. The mass of water is about 18.02. Grams is our numerator, so we're going to put the molar mass in our denominator. And that is to produce 1 mole of H2O. And now same as up here, we need that ratio of moles of water and moles of hydrogen needed to make that mole of water. The mole of water, again, needs to go in our denominator because we currently have moles of water in our numerator. And now the formula of H2O, you need 2 moles of hydrogen to make 1 mole of water. So it's a 2-to-1 ratio. And so the main difference between the work in the top and on the bottom is the molar masses and the ratios themselves. We have to multiply our molar value of hydrogen by 2 before we can get our final answer. And so this amount of water was produced by 2.081 moles of hydrogen. Now, this compound contains no oxygen, and it only contains carbon and hydrogen, so we don't need to convert either of these values to masses. There's no need to subtract because we have found both components of our compound. It's a hydrocarbon. And so if these are the only 2 elements present, and we know that all of the carbon got converted into carbon dioxide, all of the hydrogen got converted into water, we don't need to find masses and subtract to find anything else. And so in a problem where you have a hydrocarbon, where you have no third element, you don't need the initial mass of your compound because you're able to get all the information necessary from the mass of carbon dioxide and the mass of water. We're not going to touch this 12.501. all we need to do now is then go down to step 3 in our list of steps and write our pseudo formula. So C 0.8679 H 2.081. 0.869 is smaller than 2.081. And so we're going to divide both of these by 0.8679. So the number we're divided by itself is just 1, so we have 1 carbon. 2.081 divided by 0.8679 is 2.4. We do not get a clean decimal that we can round up or round down, so now we have to look at our decimal and know what to multiply by. 0.4 is the same thing as saying 2/5. And so if 0.4 as a fraction is 2/5, we multiply by our denominator here. We multiply this formula by 5, and we get our actual formula. So 5 times 1 is 5. 2.4 times 5 is 12. The empirical formula of this compound is C5H12. So this is how to solve it when you have a hydrocarbon. It's a little more straightforward. You're not having to worry about that second element being present. But now let's look at one. We're going to jump down a little bit to look at a problem that has a third element, and we need to use that mass. We're going to jump down to problem 3. So, question 3. Quinone, which is used in the dye industry. A lot of these problems end up giving filler information. So I'm just going to skip through a little bit of this. It's an organic compound containing only carbon, hydrogen, and oxygen. We have a third element that we now have to figure out how much we have. What is the empirical formula of a compound if they find that 0.105 grams of compound, so that much of quinone? I'm just going to abbreviate it as QU, gives 0.257 grams of carbon dioxide and 0.0350 grams of water when burned completely. And they also give us a molecular weight. We'll worry about that when we're done with our empirical formula. So now we do have oxygen to worry about, and so we're going to add a few more steps to this. But the initial steps are going to be exactly the same. So we start with the mass of our carbon dioxide, and we're going to convert that out of grams and into moles. 1 mole of carbon dioxide per 44.01 grams of carbon dioxide. And now again, we convert this to moles of carbon. It's a 1-to-1 ratio. 1 mole of carbon produces 1 mole, or is needed to produce 1 mole of carbon dioxide. And now I'm going to stop my calculations here because we know we're going to need the molar value of carbon later on. So 0.257 divided by 44.01. This much carbon dioxide is produced by 0.005840 moles of carbon. And now let's move on to our water. So same steps, 0.0350 grams of water. We first have to get out of grams and into moles. 1 mole of H2O per 18.02 grams of H2O. And now, like we said before, it takes 2 moles of hydrogen to make 1 mole of water. 2 moles of H per 1 mole of H2O. And so this much water is produced from 0.00394 moles oh, I'm sorry, I'm looking at the wrong number. 0.003885 moles of hydrogen. Now, we have our molar values. We know we're going to need those for our empirical formula later, but we still need to know how much oxygen we have. We can't use this same setup because oxygen is split between the carbon dioxide and the water. We don't know exactly how much oxygen went into the carbon dioxide and how much of it went into the water. And so that's when we need to use the mass values. So we're going to take our mole values of each atom and convert them to grams. Because this compound is comprised of carbons, hydrogens, and oxygens, then finding the mass of carbon and the mass of hydrogen and subtracting it from the original would leave only the mass of oxygen. And so moles to grams, we have to multiply by the molar mass of each of these. The mass of carbon is about 12.01 grams. And the mass of hydrogen is about 1.01 grams. And so 0.005840 moles of carbon is equal to 0.07014 grams of carbon, and 0.003885 moles of hydrogen is equal to about 0.00, this is the number I was writing before, 392.924 grams of hydrogen. So now we can take the mass of our original, 0.105 grams of our sample, and we subtract the mass of our carbon, and the mass of our hydrogen, I don't like it close together either. There we go. And that would leave us with just the mass of the oxygen. Now we have the mass of the oxygen. So 0.105 minus the combined masses of the carbon and hydrogen to get the mass that's left for the oxygen. And so now the last part, or the last part before we write our formula anyway, we have grams and we know that we need moles to write this formula. So now we started with moles, so we multiply by the mass to get grams. We're starting with grams, so we're going to divide by its molar mass to get moles. 1 mole of oxygen is 16 grams. And so this mass of oxygen is equal to 0.001934 moles of oxygen. So now we have moles of carbon, of hydrogen, and of oxygen. I recommend underlining stuff as you're going through the problems, just like, or like make notes of something. Don't necessarily circle anything because that might be mistaken as an answer. But if you're able to just like underline, highlight, or like make a note on the side of your molar values just to keep your numbers in order, that would definitely be helpful. But now we have all our molar values, so we can make our pseudo formula. So C, 0.005840, H, 0.003885, O, 0.001934. We have our pseudo formula. We're going to divide all of these by the smallest value. In this case, it's oxygens. Oxygens, of course, cancel out, so that'll be just 1 oxygen. But when we do our division, we don't actually have to worry about decimal places. You should just get C3H2O. Our empirical formula is complete. In this case, we didn't have to multiply by some common factor because these end up being divisible enough to get small whole numbers for our substrates. But now remember, there was a molar mass given to us. It has a molecular weight of approximately 108 grams per mole. If a molecular weight is given, we can find the molecular formula. The only additional math we have to do is find the mass of our empirical formula. So we have 3 carbons. We have 2 hydrogens. And we have 1 oxygen. We add all of these values together, and the mass of C3H2O is about 54.05. So if the empirical mass is 54.05 and the molecular mass is 108, we divide the two to get that ratio. It's always molecular mass divided by empirical mass. 108 divided by 54.05. All of the units will cancel out in this case because we're just looking for that ratio. And this gives us a decimal of roughly, or a value of roughly 2. And so if our empirical formula is C3H2O, then our molecular formula gets multiplied by 2. C6H4O2. And so that's the only additional work you have to do to finish this problem out. Compare molecular weight to empirical weight and multiply by whatever ratio you get here. This should always end up being a whole number ratio. I've never seen a problem where they give you a decimal because then you wouldn't be able to make the proper comparison. Because this work is only ever done after you get that whole number empirical formula. We're going to backtrack now to question 2, and I want to focus on this one because it is important to focus on the wording of the problems when it comes to these. For all of these questions, it's important to be able to pick through the question, know what information you need, what you don't need, but especially when nitrogen is involved, it changes a little bit how you're going to solve the problem. So, in the course of the combustion analysis of an unknown compound containing carbon, hydrogen, and nitrogen, 12.923 grams of carbon dioxide and 6.608 grams of water were measured. Treatment of the nitrogen with hydrogen gas results in 2.501 grams of ammonia. The complete combustion of 11.14 grams of the compound needed 10.573 grams of oxygen. What is the empirical formula? So they give us each of our products, carbon, hydrogen, nitrogen. They also give us information about the initial sample. The combustion of 11.014 grams of compound needs 10.573 grams of oxygen. But when it comes to problems that involve ammonia, solving for nitrogen, you don't need information about the starting sample. Just like a hydrocarbon, you don't need that information. You don't need it when working with nitrogen either, because if you notice in the problem, it says that it's a whole separate reaction. Treatment of the nitrogen with hydrogen gas resulted in 2.501 grams of ammonia. That is a separate reaction from the combustion reaction. Essentially, they took the combustion and then took the sample itself, extracted the nitrogen, and performed a separate reaction with it. Because they're performing a separate reaction, we're not going to use the information about the original compound to find information about the nitrogen. We have information given to us with the ammonia and the treatment of the nitrogen with gas, because that would essentially be hydrogen gas plus nitrogen becomes ammonia. I just need to remember how to balance this real quick. It should be, put a 2 here. that'd be 2, but that'd be 6. So you put 3 here. There. Balancing will be for a later workshop. It should actually be the next workshop after this. But yeah, when you react nitrogen with 3 moles of hydrogen, you get 2 moles of ammonia gas. Just make sure that's 6, that's 6, yeah, that's all balanced. So this is a completely separate reaction. We don't need that information about the sample. And when they talk about the oxygen, that is just a red herring. There is no oxygen in this compound, so we don't have to worry about how much oxygen was used to combust this. If oxygen was in this compound, that would change how we solve this. We would absolutely need to know information about that 10.573 grams of oxygen. But in this case, we don't need it. There is no oxygen in our compound. We don't need any information about the oxygen or the original sample. We can solve this as we would for a hydrocarbon, just with some additional work to focus on that nitrogen as well. So starting with our same steps, we want to know about our carbon and our hydrogen. We have grams of carbon dioxide, and so we're going to convert 2 moles of carbon dioxide using its molar mass, 44.01 grams. And then setting up that 1-to-1 ratio, 1 mole of carbon per 1 mole of carbon dioxide. And so 12.923 grams of carbon dioxide is produced by 0.2936 moles of carbon. Now we have 6.608 grams of water. We want to convert this into moles. So 1 mole of water per 18.02 grams of water. And then just like the carbon, we need moles of hydrogen. It's a 2-to-1 ratio, 2 moles of hydrogen for every 1 mole of H2O. This much water is produced by 0.7334 moles of hydrogen. Now for the nitrogen, we're going to do the same work we're doing here. We're just going to focus on the nitrogen containing compound. All of the nitrogen got converted into ammonia, so all of it can be used to find the amount of nitrogen we started with. Just like the carbon dioxide and the water, all of the carbon got converted into carbon dioxide, so that's why this works. All of the hydrogen got converted into water, so that's why this works. So we have 2.501 grams of ammonia. Same as always, we're going to convert 2 moles first. So knowing the molar mass of ammonia, 1 mole of ammonia is about 17.04 grams. Putting the mass in the denominator so it can cancel out. And again, looking at how much nitrogen is in 1 thing of ammonia. NH3, it is 1 mole of ammonia, and so just like the carbon, it is just a 1-to-1 ratio. 1 mole of nitrogen per 1 mole of NH3. And so this much ammonia is produced by 0.1468 moles of nitrogen. We are able to get our moles of carbon, hydrogen, and nitrogen without touching the original sample and without looking at the oxygen. Now we have all of our information to move on to our pseudo formula. C.2936, H.7334, N.1468. 0.1468 is our smallest, so we're going to divide everything by 0.1468. And this also ends up giving us whole numbers. We don't have to worry about multiplication, finding our fractions. And so this should just simplify to C, 2, H, 5, So oftentimes when nitrogen is involved, there is no subtraction with mass. The mass is not going to be important. It's all about reading the question and understanding what information is being given to you. They told us the mass of ammonia that was given, and that told us that we didn't need to worry about subtracting anything. If they told us how much ammonia we started with, and we know that all of the nitrogen is getting converted into only ammonia, then we don't need to worry about subtraction. Oxygen, we have to subtract masses because oxygen is being shared between the carbon dioxide and the water. But neither of these products contain nitrogen, and ammonia is the only product in this reaction when treating nitrogen with hydrogen. If that's the only product, then we don't have to do any mass conversions in terms of subtracting, figuring out what nitrogen went where. We are able to just convert it directly, just like we are the carbon and hydrogen. That is the end of this workshop. If there are still any questions on the content that was covered in this recording, absolutely reach out to the Math and Science Resource Center here at John Jay to get more assistance. You can book an appointment yourself through John Jay Navigate, or you can go to the tutoring center on campus, room 1.94 in the new building, and someone at the front desk can help you book an appointment. You can book one-on-ones either in person or virtually, and there are plenty of tutors here who can help you understand the content better.